Welcome to week number 12 for ECE 111. This week we're going to look at complex numbers. Now if you look at the courses you need to graduate in electrical computer engineering, just taking computer engineering as an example, you normally just use real numbers. Real numbers work fine for DC signals. Where you start using complex numbers is when you start getting into AC signals, and that's right about here. 2/3 of the way through circuits 1. You start using complex numbers, and from this point onward, we'll be using complex numbers throughout the ECE program. So electrical computer engineering, we kind of live and breathe complex numbers. They're really important. The topics that we're going to cover in this lecture would be complex numbers, of course, as well as complex numbers on an RPN calculator. Now, in my opinion, having a good calculator is worth 10 points on a test. A really good calculator, in my opinion, the best calculator ever built, was the HP42. It's no longer in production. You can find them on eBay occasionally, but it's a free app on your cell phone. Just look for free 42, and you have the HP42 calculator free of charge. It works great. Some instructors do not allow cell phones on tests. Some do. On my classes, about half in ECE, go ahead and use your cell phone. Just don't text each other answers. That's kind of why I insist that you show your work, so I can tell that you actually did the work rather than just have somebody text you the answer. If you want an RPN calculator, they're available on Amazon. The DM42 calculator is $300, kind of expensive. The HP Prime is $129. For about $20, fairly shortly, we'll have an HP calculator that you can build. Just buy kit solder together, and you'll have your own do-it-yourself calculator. They're not that hard to program. That's one of the assignments that we do in embedded systems, which is right here. That's where we actually have you program your own calculator. But regardless, you need a good calculator that's worth 10 points on a test. Tests tend to be a race. You need to get to the end quickly. RPN calculators are fast. They will dust an algebraic notation calculator like a TI. We used to have calculator races back when I went to school. The HPs would dust TI calculator. In addition, HP calculators give you the right answer. That's also worth points. So in my opinion, when you get to circuits 2, for sure, once you get to these courses right here, you really need a calculator that can handle complex numbers. Which one you choose is totally up to you. I recommend the HP42, but it's your choice. The objective of this lecture is to be able to add, subtract complex numbers, be able to multiply and divide complex numbers, be able to switch between rectangular and polar form back and forth, and be able to do partial fraction expansion using complex numbers. So, as an introduction, numbers do matter. Numbers make a difference. The existence of mathematical oddities can be determined the fate of empires. For example, the number 0 is kind of a weird number. For example, Sesame Street had an entire skit on the number 0. Here Ernie is showing Cookie Monster that there are 0 cookies in the box. This, of course, causes great confusion as to what do you mean 0 cookies? Well, 0 is a weird number. Why do you have the number 0? It's not really necessary. The Roman Empire, for example, didn't have the number 0, and Rome had a vast empire. You know that they had commerce. You know that they had accounting. You can't run an empire like that without accounting and numbers. But Romans didn't have the number 0. Instead, what Romans had is representation for the different numbers, like the number 1 was I, V is 5, X is 10, L is 50, C 100, and so on. I could represent the number 9 as IX, that'd be 1 minus 1 short of 10, XC, 10 short of 100. So the number 27, for example, would be XXVII, 10, 10, 5, 1, 1. The number 109 is CIX, 100 plus 9. So you can represent numbers just fine using Roman numerals. Problem with Roman numerals. Addition is difficult. For example, add these two numbers together using Roman numerals. Not easy. Multiplication is difficult. Now multiply these two numbers together. You know the Romans did it. You can't run an empire without addition and multiplication. It ain't easy with Roman numerals, though. In contrast, if you go with Arabic numbers have each digit represents the power of 10. So 106 means 1, 100, 0 tens, and 6 ones. With that representation, you need the number 0 because 106 is very different than 16. I need to stick that 0 in there as a spaceholder to say that there are 0 tens. Now what Arabic numbers do for you is they make addition and subtraction, as well as multiplication and division, a whole lot easier. Addition and subtraction is piece of cake with Arabic numbers. Multiplication is a little bit harder, but you can do it. Division's harder still, but way, way, way easier than Roman numerals. And that's what the number 0 does for you. It makes addition, subtraction, multiplication a whole lot easier. Again, multiplication, division is still kind of a challenge, but it's a whole lot better than Roman numbers. That's the number 0. How about negative numbers? Now, if you search Sesame Street, they talk about the number 0. They never talk about negative numbers. Probably a reason for that. Negative numbers are a really weird concept. For example, I know what the number 3 means. 3 apples would be 3 apples. 2 apples, 1 apple, 0 apples. Or in the previous case, 0 cookies really confuses Cookie Monsters, but 0 cookies represents no cookies. What does negative 1 represent? Again, kind of a weird idea. Negative numbers make some calculations a whole lot easier. For example, in the previous calculations, when we did voltage nodes, I didn't have to worry about the direction of the current. I could just say all the current from a node has to add to 0. So if this is a node has 3 different paths, these 3 currents must add to 0. If some of them are negative, that's fine. If I don't mind negative numbers, it all works out. If I don't allow negative numbers, I have to know the direction of the current to find the current, and that causes problems. So we've been using negative numbers, and that really simplifies things like voltage nodes, current loop equations. Negative numbers can also decide the fate of empires. For example, Florence was a little bitty city-state in 13th century Italy, and yet Florence was able to compete against large countries like Spain, France, England in commerce and world dominance. What did that was the double-entry bookkeeping system. They basically invented negative numbers. What the other empires were doing is when you send a ship out to sea, you ignore how much money you put into the venture, and when the ship comes back, you just get all excited about how much money you got when the ship came in, ignoring how much it cost to actually send the ship out. What Florence did is they invented the double-entry bookkeeping system where you keep track of debits, how much it cost to send the ship out, credits, how much you got back when the ship came in, and the difference was your profit. So likewise, Florence only invested in things that made money, whereas everybody else was kind of haphazard, which ventures they put money into, which ones they didn't. By only focusing on profitable ventures, Florence was able to compete against much larger countries. That's kind of negative numbers. In fact, accounting can determine the fate of empires. Back in the 1960s, the Soviet Union thought they were growing by 20% a year. The US was only growing 4% a year. And if you look at exponential growth, the US was larger than Russia back at the time. But if the US is growing at 4% growth, Russia is growing at 20% growth, eventually Russia would be so much larger than the US, they would just swamp us economically. So when Khrushchev went before the United Nations, took his shoe out and started pounding on the table, "We will bury you," that's what he was referring to. At 20% growth, the Soviet economy would be so large by 1980 that they would just crush the West economically. And they built their entire economy, built their entire military, assuming 20% growth. What actually happened is the Soviet economy was shrinking by 1 to 2% per year rather than growing. So the military that they were building, assuming 20% growth, was simply too large to support with only 1 to 2% growth or shrinking a year. So Russia basically collapsed under Gorbachev. Reasons for the, thinking 20% growth versus 1 to 2% shrinkage, reasons for that. But still, basically, the U.S. had better accountants than Russia. Reason we won the Cold War, accounting. So numbers can actually determine the fate of empires. This leads us into complex numbers. Now, for most of the curriculum, to right about here, we deal with real numbers. Real numbers work fine for DC signals. Like if I have a 9-volt battery, if I plot time versus voltage, the voltage out of a 9-volt battery is just 9 volts constant. To mathematically describe the signal, I can just use the number 9. Real numbers work just fine for DC signals. If I have currents, the current's just a constant, a real number represents that. Up through here, you do DC analysis. Once you get to the end of circuits 1, and definitely in circuits 2, you start dealing with AC signals. If you have an AC signal, you have a sine wave and a cosine wave. For a sine wave, I have two parameters. Any sine wave consists of two terms, a sine and cosine term, or in polar form, an amplitude and a delay. So I need two numbers to represent a sine wave. I can do that with real numbers, but I then wind up with two sets of equations, one for sine, one for cosine. It'd be really convenient if I could just have a single number represent a single sine wave. That's what complex numbers do. Complex numbers have two parts, a real part and a complex part. That lets me represent sine and cosine, or in polar form, they have an amplitude and an angle. That lets me represent the peak and the delay. So once you get to circuits 2, from then on, you're going to be dealing with complex numbers. And as far as I know, electrical engineering is about the only major where we live and breathe complex numbers. Anytime you're dealing with sine waves, which is like all the time, you need complex numbers. So here's what a sine wave looks like. Again, you got a sine term, you got a cosine term. A general sine wave is composed of both these together. I need two terms to represent a sine wave. That's complex numbers. Now, a generalized sine wave could be represented two different ways. I have the cosine term and the sine term. Or in polar form, I have the amplitude and the phase shift. Still, I need two numbers to represent a sine wave. Again, that's what complex numbers do for you. Now, you might think I need three parameters, frequency, sine, and cosine. Frequency isn't really a problem. If you have a linear circuit, the frequency doesn't change. For example, on your stereo, I've got a frequency coming out, your MP4 file, whatever you're playing, that goes through a filter, gets amplified, goes to the speaker. The frequencies don't change. If they change, that would be distortion. You don't want that. So I know what the frequency is. If the input is 100 Hertz, everything's 100 Hertz. What does change is the amplitude and phase shift. What does change is the sine and cosine term. So again, I need a way to represent two parameters with a single number. That's complex numbers. So in general, anytime you're dealing with DC signals, use real numbers. Anytime you're dealing with AC signals, you got to use complex numbers. Really simplifies the mathematics. So in short, ECE majors live and breathe complex numbers, probably more than any other major. That means when you get to tests and homeworks, you need a calculator that can do complex numbers. On homework, you can use MATLAB. MATLAB has no problem with complex numbers. When you get to a test, it's kind of hard to use MATLAB on a test. You need a hand calculator that can do complex numbers. And which calculator you use is totally up to you. I strongly recommend the HP42 calculator, which is a free app on your cell phone. Just search for the word free42. And that's a free app for Apple, Android, pretty much all cell phones. You can get a free42 app. Really good app, totally free. Emulates the HP42 calculator. I have not found a bug in it. It's a really good app. It emulates, in my opinion, the best calculator ever made for electrical computer engineering majors. Basically, HP is a company made up of electrical engineers. And surprise, surprise, HP builds really good calculators for electrical engineering. It deals with complex numbers with ease. It's worth about 10 points on tests. And I don't think that's an exaggeration. HPs are quick. You can get to the answer quickly, and time is points. Tests are typically a race. I got to get to the answer before time runs out. HPs let you do that. HPs also give you the right answer. I've been teaching for 35 years now, and I get kind of frustrated. People set up the equations just right and get the wrong answer. It's not the students, it's their calculator. You need a calculator that can grind out complex numbers. HPs will do that. There's a couple of versions available. Amazon sells them. On Amazon, they're called the DM42. Goes for about $300 on Amazon. A little bit ritzy. The HP Prime is the current version that's in production. About $124 on Amazon. There's also the Bison 42 coming up. Should be available summer 25 for $20. It's basically a circuit board that you solder together, and you have your own HP 42 calculator. I've talked to the instructors that teach Circuits 1, Circuits 2. They will allow you to use a calculator that you built yourself. They just won't allow calculators where you can text other people during the test. So this is allowed in Circuits 1, Circuits 2. If you're taking my classes, go ahead, use your cell phone, use the free app. But depends on the instructor. As a note, however, HPs do have a learning curve. So don't try to learn them during midterm. So to illustrate that, here is the 342. There's also an app on your computer. Really not needed because you have MATLAB. But this just shows up on the screen when I record. If you notice, there's no equals button on the HPs. HPs use a thing called reverse Polish notation. There's a stack, a 4-element stack X, Y, Z, T. When I input a number, I can push it onto the stack with 8, 7, 6, 5. So there's my stack, 5, 6, 7, 8. R down rolls the stack. You can see the elements on the stack. There's X and Y. Swap X and Y. The operations over here, they operate on the stack. When I add X and Y. 5 plus 6 is 11. 11. When I subtract, I do Y minus X. So 7 minus 11 is negative 4. Multiply multiplies X times Y. And slash is divide. 8 divided by minus 32 is negative 0.25. So it's a little bit weird getting used to. Once you get used to it, it's second nature. It's actually really, really fast. Another advantage of HP calculators, you don't have to worry about someone borrowing your calculator because no one else can figure them out. They definitely have a learning curve. What I'd recommend is in 111, get used to using your calculator. I recommend the HP 42 so that when you get to Circuits 1, Circuits 2, you're not fighting the calculator, you can focus on the test. So we'll talk more about that later. So let's get into complex numbers. One of the beauties of the HP 42 and MATLAB is they handle complex numbers just fine. With complex numbers, unlike real numbers, complex numbers have two terms. They have a real part and a complex part. That allows us to represent sine and cosine terms with a single, albeit complex, number. Now the basic idea is to define a term called J. In math, they use I. In electrical engineering, I means current. So electrical engineering, we use J. Math uses I. Anyway, pick a term. I'm going to use J. J is defined as the square root of minus 1. What that means is J squared is minus 1. If you have a number, I can represent it with two parts. I have a real part and a complex part. And the way that's drawn graphically is I have an xy plane. The x-axis is the real part. The y-axis is the complex part, the imaginary part. So I have a point A plus JB, that's A real, B complex. Now we can also represent complex numbers in polar form. That's the amplitude and the angle. Both forms are equivalent. I can convert from rectangular to polar, polar to rectangular. I can, well, polar form is also shorthand notation. E to the j theta is cosine theta for the real part, j sine theta for the complex part. It's if I have a vector at angle theta, which I'm using q here just because my keyboard doesn't have theta as an input. At that angle, the real part is the hypotenuse 1 times cosine theta. The y part is 1 times sine theta, and that's times j. So this is Euler's identity. When I represent a number in polar form, the shorthand notation is c at angle theta. What that really means is c e to the j theta, or c cosine theta for the real part, c sine theta for the complex part. That also leads to Euler's identity. Doing some algebra, I can say that cosine theta is e to the j theta plus e to the minus j theta over 2. Sine theta is e to the j theta minus e to the minus j theta over 2j. You kind of see how that works. E to the j theta gives you cosine and sine. E to the minus j theta, cosine of minus theta is cosine theta. Sine of minus theta is minus sine theta. So when I add these two together, the sine terms cancel. There's a plus and a minus. The cosine terms add, gives you 2. Divide by 2 gives you cosine. Likewise for sine. And kind of see that if I substitute, here's e to the j theta, there's 1/2. The complex parts will cancel out, and you get cosine. Now to input numbers, complex numbers into MATLAB, there's a couple ways to do that. The default value for j is I squared to minus 1. See, j squared is minus 1. I can input a number like a is 2 plus 3 times j. That gives me a complex number. I can also say a is 2 plus 3i. MATLAB accepts either way. In polar form, I can input a complex number as the amplitude times e to the j theta. So if I have b is 3 times exp of j times 1.5, that 1.5 is in radians. So it's equal to 3 times cosine of 1.5 radians plus j times sine of 1.5 radians. Oops. Times 3. And notice the two answers are the same. So you can input numbers either in rectangular or polar form in MATLAB. The default in MATLAB is polar form. So if I say C is A times B, I get a complex number. To convert that to polar form, the magnitude is absolute value, and the angle is the MATLAB command angle. It's 2.48 radians. On HP calculators, you can input complex numbers as well. So here's my HP calculator. Let's get this out of the way. There's this guy complex. If I want to input a number in rectangular form, I go Shift, Modes, Rectangular. Now if I do 2, enter 3, complex, there's 2 plus J3. 5, enter 6, complex, 5 plus J6. That's in rectangular form. If I do modes, polar, and also modes, I'm in degrees right now. I can say what is 7 at 14 degrees, 8 at 27 degrees. I input the numbers in polar form. And I can switch back and forth, go back to rectangular. 8 at 27 degrees is 7.12 plus J3.63. Switch between the two at will. Other thing the complex does, if my number's already complex, if I hit complex again, that pulls out the real part and complex part. So if I ever need to take my complex number and separate it, that's what that does. if I go to polar form and hit complex, it pulls out the amplitude and angle. So sometimes I want the amplitude and angle, sometimes I want the real part, complex part. You can do that by switching between rectangular and polar. So again, that's like how you input the number 5 at 27 degrees. 5, enter 27. Make sure I'm in polar mode. There's 5 at 27 degrees. With complex numbers, you can add, subtract, multiply, and divide. Addition is pretty easy. When you add complex numbers, the real part adds and the complex part adds. So for example, let's take 7, enter 8, first complex number, 2, enter 3, complex number. Add them together, I should get 9 plus j11. Add, sure enough the answer is 9 plus j11. When you subtract, the real part subtracts, the complex part subtracts. So 9 plus j11 minus 5 plus j8. Subtract. Real part subtracts, complex part subtracts. Now in polar form, that also works. This is where calculator is kind of helpful. If I have 5 at 17 degrees plus 6 at 33 degrees, when I add them together, it's not 11. Well, these don't add. I've got to go back to rectangular. The real part adds, complex part adds. When I add them, I get something. Not really clear what's going on. If I go back to rectangular, 5 at 27 degrees, 6 at 13 degrees, go back to rectangular, then you can see what's happening. I add the real parts, add the complex parts, go back to polar, there's your answer. The calculator does all that for you. Just hit add. I want to say, what is that? Plus 5 at 22 degrees, minus 9 at 44 degrees. No problem. So again, addition and subtraction also work in polar form. If you had to do it by hand, I would convert to rectangular form, add the real part, add the complex part. I wouldn't do it by hand. Use your calculator. Come up with a calculator that can add, subtract, coming up soon, multiply, divide complex numbers. It'll make your life a whole lot better. MATLAB, of course, will do all that just fine as well. In MATLAB, get this out of the way. Yeah, MATLAB adds, subtracts. Just fine. Let's move on to multiplication. Multiplication is a lot harder, but multiply two complex numbers. I have a1 times a2, a1 times jb2, jb1 times a2, jb1 times jb2, j squared is minus 1. So the real part is a1, a2 minus b1, b2. The complex part is j, a1, b2 plus j, a2, b1. So complex times complex is complex. And that does work out. Go back to rectangular. We take 4 plus j5, 6 plus j7. Multiply these. The real part will be 4 times 6 minus 5 times 7. Complex part will be 4 times 7 plus 6 times 5. HP has been pretty well debugged. Answer is minus 11 plus j58. Net result, complex times complex is complex. Now, back when I was in school, 30 years ago, before they had HP calculators, what we would do is convert to polar form. Polar form is a little bit easier to multiply. Rectangular form is nice for addition. Polar is nice for multiplication. If I have 2 at 17 degrees times 3 at 22 degrees. When I multiply, the amplitudes multiply, the angles add. So multiply should get 6 at 39 degrees. Multiply, poof. So this is where polar form is nice. What's happening is you have e to the a times e to the b is e to the a plus b. r1 theta 1 times r2 theta 2. What that represents is r1 e to the j theta 1 times r2 e to the j theta 2. r1 and r2 multiply. The exponents add. Gives you r1 r2 e to the j theta 1 plus theta 2, which means, shorthand notation, r1 r2 at an angle of theta 1 plus theta 2. So in polar form, when you multiply, the amplitudes multiply, angles add. To subtract, or divide, I mean. To divide, you need to use complex conjugates. A complex conjugate is take the complex part, change the sign. On calculator, HP calculator, I have 2 plus J3. To get the complex conjugate, I need to split up the parts, change the sign of the complex part, bring it back. So there I have 2 plus J3 as conjugate, 2 minus J3. A property of complex conjugates is when I multiply them, I get a real number. It's the real squared plus complex squared. And the way that works is I have the complex part is 2 times J3 plus 2 times minus J3. Those cancel. So the complex part's gone. The real part then is just a squared minus j squared b squared. J squared is minus 1, cancels with the minus, gives you plus b squared. And if I try that, multiply together, I should get 2 squared plus 3 squared, 13. And the complex part is 0. Where complex conjugates are useful is for division. So if we have a plus jb1 over a2 plus jb2, the way you do that by hand is to multiply by the complex conjugate of the denominator. That makes the denominator a2 squared plus b2 squared. Multiply two complex numbers in the numerator. I get a real part and a complex part. Split them up. There's the real part. There's the complex part. Okay, that was a lot of work. Fortunately, HP calculators do that for you. Take 2 plus J3, 4 plus J5. Take the ratio. It's this. It's a complex number. Polar form is actually a little bit neater for division. If we go to polar and do 5 at 17 degrees, divided by 2 at 11 degrees. Take the ratio, I get 5 over 2, 2.5. Take the difference at 6 degrees. So in polar form, or division is actually easier in polar form. If you have a calculator, you don't care. If you have MATLAB, you don't care. So in MATLAB, get this out of the way, I have A, B, C is A times B, not a problem. D is A divided by B. It's a complex number. What it is, MATLAB will figure that out for you. You can do it by hand if you're really glutton, but this is where it really helps to have a calculator or have MATLAB. MATLAB or the calculator will do the work for you. So here's a problem. Find the solution to these problems. I want to add, subtract, multiply, and divide complex numbers. So let's pause the video and have you solve those. Then we'll resume in a little bit. So resuming, addition's easy. 2 plus 9 is 11. 3 plus J4 is J7. I don't need a calculator for that. I could use a calculator. 2, enter 3, complex. 9, enter 4, complex. Here's my two numbers. Add them together. Surprise but surprise, 11 plus J7. Subtract. 2 minus 9 is minus 7. 3 minus 4 is minus J1. So let's try that. 2, enter 3, complex, -9, oops, try that again, 9, enter 4, complex, subtract, you get -7 minus J1. Multiply. I'm not even going to bother. It's 2 times 9 minus 3 times 4 for the real part, 2 times 4 plus 3 times 9 for the complex part. Or here I'd use my calculator. 2, enter 3, complex, 9, enter 4, complex, multiply, 6 plus J, 35. I could check the answer. This app is pretty well debugged. Take the ratio. 2, enter 3, complex, 9, enter 4, complex, divide. It's a complex number. Now, here's a problem that you're going to run into in electrical engineering, especially when you get to circuits 2. Solve this. This is where you really need a calculator that can handle complex numbers. Take a little bit of time to solve this problem. Now with the calculator, what I would do is input the numbers. 2, enter 3, complex, here's the first number. 4, enter 5, complex. Multiply these two together. Take the number 6 plus J7, 6, enter 7, complex. Now add them. Divide by 8 plus J9. There's your answer. I can do that in MATLAB. In MATLAB, put it down here. Y is equal to 2 plus 3i times 4 plus 5i plus 6 plus 7i. And I need parentheses here. Take that whole mess, divided by 8 plus 9i. And I got a different answer. Oh, that's because I input the wrong problem. 2 plus 3i, 4 plus 5i, 6 plus 7i, 8 plus 9i. There we go, same answer. I could do that by hand. Really painful. Multiply complex numbers, then add them, then multiply by the complex conjugate, divide, get the answer. MATLAB is way easier. That's why we use MATLAB. HP calculators are pretty easy too. And there's the sequence for the HP calculator. Okay, let's do partial fraction expansion. Now this is a pretty common trick that we use in several different courses. If I have a polynomial like this, or a fraction, I can represent it as 3 terms. And the idea is equals is really powerful. These two sides are identical. As x goes to -1, this blows up to infinity. As x goes to -1, this blows up. This is a constant, that's a constant. Constant relative to infinity doesn't matter. So as x goes to -1, these have to match. Canceling out these terms, as x goes to -1, a must be this one. That's called the cover-up method. What I do is I evaluate this at, to find a, cover up this term, plug in x equals -1, evaluate, that's a. So again, what I would do, let's use MATLAB first. In MATLAB, if we can find MATLAB, there it is. I would say x is -1, a is 2 times x plus 3 over x plus 2 times x plus 3. A is 0.5. To find b, I let x be -2, and then b is 2 times x, let's do it this way, b is 2 times x plus 3 over x plus 1 times x plus 3. I cover up the x plus 2 term. That's b. Define c, plug in x equals minus 3. And then c is 2x plus 3 over x plus 1 times x plus 2. There's c. 0.5, 1, minus 1.5. I can do that on an HP calculator. So like if this is a test, I don't have access to MATLAB, I can do the same thing. I would take -1, store it in x, and to store in a variable, I would do store, and I've created x before. If I want to create a new variable, I would do alpha, let's call it z. I now have a variable z that I can pull back. I've already got an x, so let's have -1, store it in x. A then is 2x plus 3, 2, recall x, multiply, add 3. There's 2x plus 3, divided by x plus 2, recall x, 2 plus slash, divided by x plus 3. Recall x, 3 plus divide. A is 0.5. To get b, b is when x is minus 2. So let's take -2, store it in x. B then is 2x plus 3, 2, recall x, multiply, 3 plus, there's the numerator, divided by x plus 1, recall x, 1 plus slash, divided by x plus 3, recall x, 3 plus slash, b is 1. Likewise for c. So that's partial fraction with real poles. Another way to do it is to put everything over a common denominator, multiply everything out, solve for a, b, and c. I get 3 equations, 3 unknowns. That's another way of doing it. I can solve that using matrices. That is a lot of work. Another way to do it. When I do that, I set up the matrix, solve, and I get the answer is A inverse times B, 0.5, 1 minus 0.5. Another way to do it. That's the way to do it if you're really glutton for pain. I would use the cover-up method. And there the idea is, again, as x goes to -1, these have to match up. The other terms are constant. This goes to infinity. Infinity relative to the other terms. These other terms don't matter. To cover up this guy right here, A has to be that. Likewise at -2, -3. Either method works. Take your choice. I use the cover-up method. It's a whole lot easier. But what you do is up to you. And the cover-up method also works in MATLAB. Third way to do it is I take the limit as x goes to -1. I can't plug in -1 because then I get 0 over 0. MATLAB doesn't like 0 over 0. So take a point that's epsilon away. Take your system times x plus 1 and you get the right answer. Take the point -2. Epsilon away. Take your system times x plus 2. -3, epsilon away. Any of those three methods work. So with that, find the partial fraction expansion for this term. Okay, let's use MATLAB. If x is -5, then A is 10 times x plus 2 divided by x times x plus 10. That's using the cover-up method. To get B, I'll cover up the x term. X equals 0 for B. B is 10 times, let's do it this way, arrow up. b is 10 x plus 2 over x plus 5 times x plus 10. You cover up the x term. There's b. For c, x is equal to minus 10. And then c is 10x plus 2 over x plus 5 times x. 1.2, 0.4, minus 1.6. And it gets the same answer if you use the HP calculator. Okay, that's with real numbers. Suppose I have complex numbers. Now, different instructors do it different ways. My preference is, if you don't mind complex numbers, do exactly what you did previously, only now with complex numbers. So, for example, if I want to find a in this case, I have x is minus 1 minus j3. A is 5 times x plus 7, that's the numerator, divided by x plus 1 minus j3 times x plus 5. There's a. To get b, b is the second term, so x is minus 1 plus j3. In the cover-up method, the numerator is 5x plus 7, denominator is x plus 1 plus j3. There's b. And for c, x is minus 5. X plus 1 minus 3i. So again, if you don't mind complex numbers, partial fractions works just the same as before. HP calculator will show that as well. On HP calculator, I'll just do one of these. We have x is minus 1 minus j3, so here's negative 1, negative 3, complex. Store x. Again, HPs don't care. To get a is 5x plus 7. 5, recall x, multiply 7 plus, divided by x plus 1 minus j3, recall x, 1, enter negative 3, complex, add those together, divided by x plus 5, recall x, 5 plus slash, same answer. So again, if your calculator can handle complex numbers, I can do partial fraction expansion as well. So I can solve in MATLAB. I can solve in HP. Last thing to cover is you can do other things with complex numbers. I can take the log. I can take complex number to a complex number. Again, HPs don't care. If I have 2 plus j3, raised to 4 plus j5, there's the y to the x command. There it is. I get a complex number. I can do that in MATLAB. Y is 2 plus j3 to the 4 plus j5. There we go. Same answer. If you want to do that by hand, it's a little bit trickier. I have to take the rectangular form, convert to polar form. So when I raise it to a power, 2 plus j3 is e to the 1.28 plus j.98. When I have e to the a to the b, the exponents multiply. Take the real part, that's the amplitude. Complex part has a real complex part. Yada, yada, yada. Or just trust your calculator. Calculators do it right. MATLAB does it right. You can do things like cosine of 2 plus j3. To enter 3, complex, cosine. HP's handle is just fine. Other calculators tend to struggle. I think the TIs work if you're in radians mode. They don't work in degrees mode. If you want to do that by hand, I have to convert to Euler's identity, multiply it all out, get something. Long, painful way to do it. Or just use your calculator. Or use MATLAB. So it works with an HP. Works in MATLAB. I can take the log of complex numbers. 2 plus j3. Take the log. It's a complex number. Where that comes from is represent that in polar form. Represent that as an exponential. Log of an exponential is the exponent. Works in MATLAB. Works with an HP. So here's a handout. The handout is try to find the answer to the following problems. And the practice problems are in the handout. Again, to solve these, use MATLAB, use an HP calculator. Answer should match up. So net result is pretty much anything you can do with real numbers, you can do with complex numbers. You can add, subtract, multiply, divide, sine, cosine, x to the y, natural log. All works with the real numbers, all works with complex numbers. Second thing to note is when dealing with complex numbers, it really helps to have a calculator that can work with complex numbers. MATLAB works with complex numbers. HP calculators work with complex numbers. If you're having a test, you need a calculator that can handle complex numbers because you really don't want to do those by hand. Get a calculator that can handle complex numbers. Get used to it. Get familiar with it so that by the time you get to circuits 2, you can grind out the numbers on tests. And if you're going to use an HP calculator I recommend, get used to it before you take circuits 2. It's got a learning curve. It's not something you want to learn during the test. Once you get familiar with it, though, they're fast. They work really, really well. So in summary, complex numbers allow you to represent something with 2 degrees of freedom, like sine and cosine. Addition, subtraction, multiplication, and division all work with complex numbers. Calculations using complex numbers by hand is really, really painful. Calculations using complex numbers aren't that bad if you use MATLAB or an HP calculator, but again, there's a learning curve. Get familiar with the calculator before you get to circuits 2. You're going to need it. What calculator you use is totally up to you, but you need a calculator that does complex numbers by the time you get to circuits 2. You need that on the tests. And with that, that is week number 12 for ECE 111.